Good Monday AP Calculus. Well, if you're watching this video, that means I didn't make it back this week. I'm probably going to need another week off for whatever reason. I don't know. We'll have to see. But hopefully I'll be back next Monday. In the meantime, class must go on. So we finished up Chapter 3, did the Chapter 3 test. Chapter 3 test was kind of a toughie, I know. It only had the 3 parts to it. The second part I combined together, the short response, calculator, non-calculator, I combined it all into a calculator part. That's why there was only one part there. And as soon as that gets graded and entered, you'll have a chance to do corrections on that for a better grade, just as normal. Everything else will proceed just as normal. But for right now, we're going to move on. We're going to talk about Chapter 4, which is applications of differentiation. A lot of different applications of the things that we've been doing. Chapter 3 was all about differentiation and differentiation rules. We did some applications and some things in there and talked about some things. But in Chapter 4, it's all about the different things that the derivatives will do for us. We will see a couple of new concepts, a couple of new ideas along the way, but mostly it's just applications, taking things that we already know and applying it in a different way. Today's example is a perfect example of that. The idea of maximum and minimum values. We kind of already know the maximum, minimum. Back in college algebra, we called them optimal solutions, optimizing things, the biggest area that a farmer can make with a certain amount of fencing, or the smallest amount of costs associated with something, or the shortest distance between a point and a curve, and there's a lot of application problems here. But with calculus now, we can do a lot more examples. So for the first part of today's lesson is going to be kind of conceptual, and then the second part we'll look at some examples. All right, so here we go. So, concepts. Let's talk about maximum and minimum points. So, Chapter 4, applications of differentiation. And of course, we know applications means word problems, right? And we're going to see a lot of word problems in this chapter. A lot of how do we do this and how do we do that. But it starts off pretty easy. The idea of maximum and minimum values. And I think we already know the whole idea behind a maximum and minimum values. If I take a look at a graph and I have some sort of function, and just looking at this function, we already know a lot of things about this function. We know, for example, that it would be 4th degree. It has 3 bends in it. And we know the lead coefficient would be negative because the end behavior is down. But I want to take a look at maximum and minimum values. And notice I seem to have a maximum value here, a minimum value here, and a maximum value there. We can greater qualify these by using the terms absolute and relative. This minimum is only a relative minimum because the function does get smaller than that somewhere else. This maximum is a relative maximum because there is a bigger maximum. This maximum, however, is an absolute maximum. The function never gets bigger than that. So we often talk about absolute and maximum. Sometimes instead of absolute, they'll use the word global. Absolute or global maximums or minimums. And a lot of times when we talk about these values in general, we talk about them as extreme values. Or extremum points on a curve. Extremum points on a curve. I do want to start with, I think that if we look at some functions, we can easily tell relative and absolutes. And if I give you a graph and tell you to find it using the calculator, I should be able to give you a function and put it on the calculator and you should be able to mess around with the window until you can see what it looks like, and you should be able to find all the maximum and minimum values on a calculator. So I'm not going to do an example of that. I want to jump right into a calculus theorem that's going to help define this over an interval. So this is called the extreme value theorem. And the extreme value theorem basically says this, that if some f of x is continuous over some closed interval, so if f of x, some function of x, is continuous over a closed interval from a to b, then, so think about what continuous and all the implications of continuous means, then the function has an absolute maximum value and an absolute minimum value on that interval from A to B. Now, the idea here is continuous. And I know you might be thinking about things like asymptotes where it goes to infinity and there is no maximum or minimum, but that would be a discontinuity, so that would be a problem. That would not apply here. So if I think about it graphically speaking, let's take a look at an example of a graph. So I want to have some sort of closed interval. So I'm going to have from A to B, and my function has to be continuous between these 2 points. So for example, I could have something that looks like, like this. And pretty much obviously we can see that the minimum would be the endpoint here, A, and the maximum would be the endpoint at B. So the maximums and the minimums, the absolute maxes and the absolute minimums, can be at the endpoints, but they don't have to be. Take a look at this example. Again, closed interval, A to B. And this time I have some sort of A here and some sort of B here. And I could have a function that does this and then does this and then does this. Again, you can see that there is an absolute minimum and an absolute maximum. They're just not occurring at the endpoints. So it may occur at the endpoints, it might not occur at the endpoints. And of course, I could have something where, if I had like a big W, I could have multiple maximums or something like that. It has to be, the interval has to be a closed interval in order for the extreme value theorem to apply. Now, if we take the extreme value theorem and the idea that at these extremum points, so here is an extremum point, here's an extremum point, here's an extremum point, here's an extremum point, what do I know about the derivative of the tangent line? What do I know about the slope of the tangent line at those points? Yeah, that's the key. That's Fermat's theorem. So Fermat's theorem yes, this is the same Fermat. Fermat's theorem says that if some function f has a local max or minimum, and of course that could be global as well, or absolute max or local minimum, at some point x equals c, and if the derivative at c exists, then, and you can guess what's going to happen here, the derivative at c has to be 0. the slope of the tangent line has to be 0. The textbook has a proof for this, but this is going to give us a very nice and quick and easy way to find these extremum points. All we have to do is take the derivative of the function and set it equal to 0. And if Fermat tells us that if the derivative is equal to 0, whatever points the derivative equals to 0, that's where I have my maximum and my minimum values. So this becomes a very important part of finding maximums and minimums, because now we can just do it with using derivatives. And I'm sure it's something we've already thought about and kind of considered. When we look at these, there's another definition too that I want to talk about, another word that I want to throw at us and use. We'll often talk in terms of thinking about things called critical numbers or critical values. Critical numbers or critical values. A critical number or a critical value of a function is some number, we'll call it C, in the domain of the function so the critical value C is a critical value if C is in the domain of the function such that the derivative at C is equal to 0, or the derivative at C does not exist. So obviously in this case, Fermat tells us that that's where we have our maximum or our minimum values. But here, it can also be a critical value if the derivative does not exist. And think about the times where it might not exist. Now notice, this does not hinge on the whole continuity thing. So we can start talking about corners and cusps. We can start talking about jumps. We can start talking about holes in our graphs. We can start talking about asymptotes and things like that. Those become critical values. And when we're going to be looking for critical values and exploring whether the critical value is a maximum or minimum value. Does the derivative there equal to 0, or is there something else going on? All right, what I'd like to do is I'd like to pause the lesson here, and when we get back, I want to take a look at finding absolute maximums and minimums and taking a look at a couple of specific examples in the next part of the lesson. So we'll get a little bit more specific. We're going from the general ideas right now into something a little bit more specific in the next part of the lesson.